All right, so I wanted to say another word about this last part of this question, just to make sure that we all understand how to convert elapsed time into calendar time. So we found the answer to this using Calc Intersect, and that answer was 24.32 years. The question, in case you've forgotten, was this: use the model to predict the year when the population will reach 600,000, and our model that we found was right here. Okay, so we got our answer in a fashion. We got the elapsed time of 24.324, but the calendar year for this is starting at July 1st. Let's go back. 2000. So plus 24.32 of a year. Okay, so the 24, that would of course put us into 2024, but then we have that would be in July 1 of 2024, but then we have 0.32 of a year after that. So the explanation for the problem says the remaining 0.34 years is less than half a year. It follows that the population reaches 600,000 in 2024. So the idea there is that 0.32 is less than 0.5. And 0.5 of a year would, if I met or exceeded 0.5 of a year, I would, since I'm starting in July, and July is exactly halfway through, that would push me into 2025. So any value that's less than 0.5 will keep me in the year 2024, since I'm starting in July. And 0.32 certainly keeps me within 2024. Okay, so there is the final part of that question. All right, so we're going to move on now to a new subject. It's still related to linear functions, of course, but this is sort of a broad subject that we will return to in other chapters, and that's the idea of an inverse function. Now, we're just kind of scratching the surface of inverse functions here. This can be sort of a deep subject, but we're not going to go too deep into it. So what is an inverse function? Well, actually, let me draw a picture to kind of give you an idea. So if we have a function that takes, let's pick a couple of values. Okay, so let's say we have a function f, and it takes 1 to 6 and 3 to 11. So f of 1 equals 6, and f of 3 equals 11. And this is just a very limited function with only a domain of 2 values. So the associated inverse function for this would basically run this backwards. So if we went this way, and we went this way, let's actually call that function, just for a moment, let's call it g. Let's say we have a function g, and g of 6 equals 1, and g of 11 equals 3. Then notice that g kind of undoes f. Okay, so we're going to have to use a little bit about the idea of function composition here to understand this. And here's the idea. If I take g and I put it into f in this fashion, then when I say they undo each other, what I literally mean is that this x value, whatever it goes to under g, f sends it right back to where it started, and vice versa. G of f of x also gives me x. So these functions completely kind of undo each other. And in this case, we call G the inverse of f, the inverse function of f. And we give it a new name, or a new symbol, sorry. F with a -1, and that's not an exponent. That's meant to symbolize the inverse function. So instead of calling this G, we would actually call this F inverse of x. Okay. Now going back to this slide. The first line here says, if the graph of a function passes the horizontal line test, then there's an inverse function. Let me explain what's going on with that and why that's important. And actually, I think I'm going to go back to my picture to talk about that. Sorry. So how could we have a problem here? So here's how we might have a problem. Suppose I had a function f. So let's draw kind of a line here. Let's say I have a function f, and this is fine. I have a function f, and it takes two values to the same output. So let's say that's 1, 3, and 5. Okay. So f is fine. F is a well-defined function. But if I try to run this backwards, right? What are we going to do? So f inverse in this case doesn't exist unless we kind of finagle things a bit. But it doesn't exist because f inverse of 5 would be equal to 1, or f inverse of 5 could be equal to 3. And so we have one input with two outputs. So the inverse function, we have a problem with the inverse function, okay? But we don't have a problem with the regular function. So the graphical analog of this is what we call the horizontal line test. And this is how you tell if a function has an inverse. So remember, we already had the vertical line test, and the vertical line test is about, is it a function? The horizontal line test is, does it have an inverse? So for example, this is a function, but it does not have an inverse. Because it does not pass the horizontal line test. And the horizontal line test is exactly what you probably imagine. If a horizontal line intersects the given graph at more than one point, then the function does not have an inverse. So I'll say that again. If any horizontal line intersects the graph of the function more than one time, then we do not have an inverse. Now, the idea is just that we're really just turning the vertical line test 90 degrees in order to kind of run this backwards to see if it will work. Okay, so that's the horizontal line test, and we'll come back to it in a moment. But in this immediate context, what's really important about this is that linear functions, as long as they're not horizontal, they have inverses. So all linear functions have inverses except horizontal lines. So the nice thing about that is that if you're looking at a function and it's linear, then you know it has an inverse, unless, I'll say it one last time, unless it's a horizontal line. Okay. Now, how do you actually find it? Well, we're going to do that right now with this example. because there's a nice easy procedure for finding the inverse of a linear model. In general, finding the inverse of a function can be quite difficult, but for linear functions it's pretty easy. So here's how we do it. So let's suppose that we're using the same population model that we found in that previous lecture, and we want to find the inverse, and we'll get to this question in a moment. But so we're going to try to find P inverse. Oh, I'm sorry. Actually, let me not name it just yet. Let me just show you how to find it. So here's what we're going to do. We're going to solve this function for t. So I'm going to say P minus 375 equals 9.25t. Then I'm going to divide both sides by 9.25. And so now I have t. Let me turn it around. So I can always just kind of flip this. Now I have t written as a function of p. And that's my inverse function. So now I can put in a population and get out a time. So in this question it says, use it to determine how long it takes for the population of the city to reach 600,000. Well, we can now plug in 600 here in our model and calculate the output. So if we're going to do this in the calculator, I would have to re-enter this as a new function. And p would now be the x variable, okay? Although we already have found this answer. I mean, don't forget, we actually did this already. We did calc intersect and we found it. But now if you plug this in, you'll see that you still get 24.32, doing it the algebraic way rather than the calc intersect way. All right, so that's a little bit about function inverses. Here's another example. Finding the inverse of this d of t function. So again, we start off d equals negative 19.4t plus 12.1, subtract, and then divide. Okay, and that's our inverse function. Again, I could rewrite this as t of d equals d minus 12.1 over negative 19.4. And there is our function. So if we want to find t of 0, which that was the question, use it to determine the length of time of my commute. So the length of time of my commute, if you can figure out when your time from home is 0, I'm sorry, when your distance from home is 0, then you can get your commute time. So here I'm plugging in d0, that's a d, so that's when I get home, and the output will be 0.62 hours. All right. So I think this is a good place to pause the video. When we come back, we're going to move on and talk more about linear functions and a new form of a linear function.